Hello, welcome to Math 251, Calculus 1 here at Cañada College. My name is Lapuz and I'm the instructor for the course. In this video, we will dive into section 3.6, the chain rule. The infamous chain rule. So the basic idea here is to be able to state and use the chain rule for finding the derivative of a composition of two functions. And then we're going to use it alongside with the power rule and come up with a modified power rule. We're going to apply the chain rule alongside with the product rule and the quotient rules as well, and making sure that the combination of using those rules and the chain rule would work out. We're going to take a look at the chain rule for three or more functions, so we're not just restricted to finding a composition of two functions, but this can also be applied to three or more functions. And then the book will go over kind of a quick proof of the chain rule. All right, so basically the idea behind the chain rule is that when you're taking the derivative of a composite of two functions, and when you're taking the composite of two functions, there's an inner function and an outer function. So this is saying that the derivative of the composite of two functions is going to be the derivative of the outer function, and that has to be evaluated at the inner function times the derivative of the inner function. And so it's a derivative times another derivative of something. And we usually say the derivative of a big function times the derivative of what's inside. Now, taking the derivative of the big function, it's important that you note that f prime here has a g of x inside of the f prime. So you're evaluating that at the inner function itself before you take the derivative of the inner function. You can also use Leibniz notation for the chain rule, and what I would caution you is to not look at this and say dy du times du dx, so the du's cancel. So there might be times where that might be convenient for us, but that is not the way Leibniz notation works. And in multivariable calculus, you'll see that there is going to be an issue if you try to approach it that way. So once we have the idea of the chain rule, here is a nice step-by-step problem-solving strategy where, in order to take the derivative of a composition of functions, you identify the two functions that you're composing and figure out what the inner function is and the outer function is. And then you take the derivative of the outer function first, and in step 2 here, make sure you evaluate it at the inner function g of x. And then take the derivative of the inner function g of x, and then you multiply those results together. Now, sometimes when we do the power rule, this is probably one of the most common uses of the chain rule, is applying it alongside with a power. And so this would be especially handy if you have let's say you have the square root of a function, the square root of x squared plus 5x plus 2 raised to the third power. Now, one way to take that derivative is to FOIL it out 3 times, and that would be a very long polynomial, and then you can just take the derivative term by term. But you can keep it combined there and use the power rule along with the chain rule. And so if you have something raised to the third power, it's going to be 3 times that something does not change. Raise it to the 3 minus 1 power. And then the chain rule tells you to take the derivative of the inside. So that's the g prime of x that happens. So it'll be commonly used where we will be looking at a power of something or an expression, a function being raised to a power, where we'd have to take the derivative of that, and we would use a chain rule. Now, one of the other objectives talks about the chain rule of 3 or more functions, composition of 3 or more functions. And so in this particular example, if you have k, and that's a composition of h, f, and g, then you simply work from the outer function and go inward. And think about it as an onion. You're peeling an onion, you peel a layer, and then now you have another derivative of the inside. You peel the other layer and you keep taking derivatives until you're done. So in this case with three functions, a derivative of k is going to be h prime. Now you have to evaluate h prime at f of g of x, though still the function that's inside has to remain on the inside. And once you do that, you take the next layer, which is f prime of x, and that is evaluated at g of x. And then the innermost layer is g, so the derivative of that is g prime of x. So it's like applying the chain rule twice, and if you have more functions, then you keep applying until you keep taking the derivative of the inside until you get to the innermost function. And then so all the derivatives that we've learned so far can follow up with the chain rule. So the power function is a common derivative that we have, and that can be applied with a chain rule. And the trig functions as well. If we have a trigonometric function, and instead of g of x, instead of just a regular x inside of the sine function, let's say you have something more complicated like e to the x, or like 5x squared times 2, or 5x squared plus 2. And so the derivative of that would just be the derivative of sine, which is cosine. Again, you have to evaluate it at the inner function times the derivative of the inside. So that's when the g of x comes in. Okay, you can see the chain rule notation for these basic derivative formulas with a g of x, or sometimes you see it with a u. Imagine doing a substitution where you let u be the inner function, and then so it'll just be cosine u times the derivative of u with respect to x. Okay, again, Leibniz notation is useful sometimes, and if you see this more than composition of two functions, you can also see that happen with the Leibniz notation as well. Okay. Here is the proof that they present in the textbook, and so it's just going to be good to walk through it. Like some of the proofs, sometimes they do some weird things, like in this case in the second step, they decide that they multiply top and bottom by g of x minus g of a, and so that's where that comes from, and then they rearrange it, and then now they take a look at each of those components, and then take the limit of each of those separately, and then you'll see the pieces that happen together. There's another proof of this that might be a little bit well, I guess it depends. If we had studied differentials a little bit earlier and in more depth, and then the proof of this might come out a little bit neater with by using differentials, but we're not using that. So I think this would be just good to look at and try to understand it, and try to see where the pieces are coming from to see how the chain rule actually works. All right, that's it for this section. Chain rule is a really important rule for us to remember, because there's a lot of times the derivatives that we're taking are composites of functions, and so that's it. Good luck.